So there are likely to be lots of questions, but yeah, Lynette, just be patient with us. I told you they're a bunch of nerds. They're very over-enthusiastic about what they do. That being said, Lynette is no longer working at the South African Weather Service. She no longer works as a meteorologist or a forecaster, but she is actually now a doctor of meteorology. And she is passionate about local factors rather than just the whole big climate thing, whatever. So I think she's a good fit. Be nice. I did ask the crew leaders for questions that we could ask, typically questions that people have asked crew leaders, and the crew leaders themselves kind of made some shit up on the go just to make it look like they knew what they were doing. And now we have an expert, Lynette.
Thank you, John. Everyone. I've been a weather forecaster for 15 years, so I pride myself on my thick skin, so bring it on. It's okay. Yeah, it's also just a privilege to be able to talk to you today, and I think the work that you do is incredible, and so if there's any way that I can support you through information or resources, then please just give me a shout. That's my email address over there. And yes, as John said, I am interested in the smaller scale weather phenomena such as thunderstorms. That was part of my research. We used lighting data and satellite imagery and also station observations, so to determine where thunderstorms develop, why they initiate, especially along small scale boundaries in air masses. So that's what I've been working on over the past few years. But I have a background as a weather forecaster, so I'm generally interested in anything that's related to weather. So I received a lot of questions from the floor, and I decided that it's maybe good to start with a zoomed out view, looking at seasonal scales and climate, and then slowly work our way towards a more local scale, looking at Cape Town's weather, things that influence our weather. So just to talk about scales, meteorologists and climatologists have different focus. So climatologists will typically look at the seasonal scales and try to establish what's going to happen in the next season, while meteorologists look at the smaller scale. The synoptic scale would be where we see mid-latitude cyclones or cold fronts. These are systems that are maybe 1,000 kilometers long. They take a few weeks to develop and run their course. But then you get shorter scale or smaller scale weather systems, such as, and that's the scale that we refer to as the mesoscale. So that's anything larger than a thunderstorm and smaller than a cold front or a tropical cyclone. So lots of weather falls on that scale. Mesoscale convective systems, larger thunderstorm systems or thunderstorms themselves. And then you have even smaller scales like the microscale, where a tornado that's much smaller than the actual thunderstorm forms, or water spouts and land spouts. And fire weather would fall in between all of those, because a cold front can advance and it can result in conditions that are conducive to fires running away. But you can also have thunderstorms that cause lightning strikes, start a fire, and then fires also they are affected by microscale gaps in the mountains, valleys. So small scale influences also affect the fire weather. So let's start with a look at what seasonal forecasts are about and why. I've received questions. Why are they wrong so frequently, and why can't we really get the hang of it? But the answer is because we have a very chaotic system. Earth system influencing climate is very chaotic. So when people do seasonal forecasts, there are different variables that influence what the season is going to be like. And one of these are ocean temperatures. So we all know about El Nino and La Nina. What are the ocean temperatures near the Central Pacific to the west of South America? But there's also the Benguela La Nina. That's also sea surface temperatures along the coastline of Angola, so the tropical coastline in the Atlantic. We have the Southern Indian Ocean Dipole. That's temperature differences between Australia's Indian Ocean and Africa's Indian Ocean. what are these doing? Even the sea ice extent. Some scientists have found that the sea ice extent from year to year, that has an influence on what rainfall is like in Cape Town. So there are so many different things. One of the things that also influences the climate here is SAM, or the Southern Annular Mode. And so I'll look at those two just to give you a brief idea of what kind of influences South Africa's weather, but there are others. So we are familiar with El Nino and La Nina. Typically, if we hear there's an El Nino on the way or El Nino developing in the Pacific, then the media runs away with stories that there's going to be a drought in the summer rainfall area. But that's not always the case for the entire summer rainfall area. Sometimes we still have above normal rainfall, and then the seasonal forecast is wrong again. La Nina is typically associated with the high amounts of rain, but for the summer rainfall area. So El Nino and La Nina doesn't really affect our winter rainfall region. So that's when we investigate the Southern Annular Mode. So I'll just explain this with, this is now a picture of Australia, but the same story applies. The Southern Annular Mode doesn't have to do with sea surface temperatures like El Nino and La Nina, but more with pressure differences. So in years when we have a positive SAM, a positive phase of SAM, that means that the pressures are generally higher to the south of our continent and to the south of South America and Australia. And that means that we get cold fronts less frequently, and these fronts are typically also not as strong. So the pressures are a bit higher to the south of us. That's a positive phase and bad for winter rainfall. But a negative phase is better because then the pressures are lower to the south of us. So that means that the low pressure systems are deeper, stronger cold fronts, and maybe more frequent cold fronts. So this is one of the influences of our climate that has been nailed down, but there are many more, and so it really is a chaotic forecasting system, and that's why seasonal forecasts, especially for the winter rainfall area, are notoriously bad. And I think climatologists will admit that. So the one thing that we can say for certain about seasonal weather is that it's extremely variable. That is the one thing that we can say with certainty. And you will know this from living in Cape Town. Just looking at these graphs, you can find them on the Climate System Analysis Group. They are at UCT as well. And they have these nice accumulated rainfall graphs. So we remember the day zero drought. That was between 2015 and 2017, where we had very low annual rainfall amounts. But just the year before that, there was quite a good rainfall season in 2014. 2013 had above normal rainfall. Then it was followed by these 3 dry years that almost resulted in dams drying up completely. It's not even a decade later, and now we've had 2 off-the-chart rainfall winters in the past 2 years. So there's extreme variability when it comes to the rainfall, and that's not just for Cape Town, it's also for the rest of South Africa. So the one thing that we do know, even though rainfall is so variable and it's very difficult to tie down whether rainfall is increasing or decreasing in the southwestern Cape, the one thing that has been shown with trends looking at rainfall data of the past couple of decades, data that's available, is that the early winter is starting to become drier, and that's been shown with research. So there's a decreasing trend in April and May rainfall. And just since 2000, we've had 5 of the 6 driest early winters on record. So there's a drying trend for April and May, and there's also a warming trend. So the past 8 April-May periods have been substantially warmer than the average. So despite the very recent wet winters that we've experienced, there is a trend that the early winter season, or autumn, is starting to become drier and warmer. And when John spoke to me before this talk, he said that you are experiencing a longer fire season because autumn is now becoming part of your late summer firefighting season. It's becoming drier and it's becoming warmer. And despite the fact that there is that it's difficult to tie down the rainfall trends over the southwestern Cape. The projections for the extreme, for the future, decades from now, between 2040 and 2060, is showing that there's a drying trend. So if we look at winter rainfall in total, and we take away rainfall from the early winter, then we are going to see a decreasing trend in rain. So that is something that that seems to be happening for sure. So now we've looked at climate. Let's start to zoom in a little bit over Cape Town and the southwestern Cape. So we are mostly familiar with the climate here, the rainfall during the winter months between May and August. There's a large variability in rainfall amounts, especially close to Table Mountain. We see amounts annually above 1,000 millimeters, but further away at the airport, only about 500 millimeters of rain. And then on the west coast, even less than that. So 200 millimeters of rain is more or less what you get along the west coast. So away from the topography, we actually get low rainfall amounts. Then there's also fog. Of all the international airports in South Africa, Cape Town receives the highest number of fog days. So the months with the most fog and the highest frequencies of fog would be May. So May is the month with the highest frequency of fog at the airport, and then it decreases as we head towards the early summer again. And quite interestingly, thunderstorm frequencies almost follow the same curve as the fog frequencies. So the highest number of thunderstorm days also tend to occur in autumn, and then it decreases towards the early summer. So very few thunderstorms actually occur in summer in the winter rainfall area. There are on average about 7 thunderstorm days at Cape Town International. And now we'll take a closer look at what the lightning climatology is like. So I'm not sure if you are aware, but South Africa is equipped with a state-of-the-art lightning detection network. There are about 27 lightning detection sensors in South Africa and in Swaziland, and they are able to detect mostly cloud-to-ground lightning strikes. So what we see here is a frequency of lightning flashes across South Africa between 2006 to 2017. In the next graph, or the next picture, I'm going to show you lightning strokes. So that's slightly different. A lightning flash consists of about 4 strokes. So the frequencies will look a bit different. Here we see over the Western Cape, we see 0.02 to 1 lightning flashes per square kilometer per year. So that's what we're looking at here. But over the eastern parts of South Africa, extremely high lightning frequencies. That's one of the regions in the world with the highest frequencies of lightning per square kilometer. And also look here at the southern parts of Gauteng, where Johannesburg is. That's one of the cities in the world with the highest lightning flash rate in the world. So we really see a lot of lightning over the summer rainfall area, but very little in comparison over the Western Cape. Now this is breaking it down in months so that we can see when lightning tends to occur most frequently. So it's no surprise that it starts in summer over the Highveld. And but what's quite interesting is that for the southwestern Cape, the highest frequency of lightning strokes happens during the autumn months. So that's February, March and April. And like I said, lightning strokes are what makes up a lightning flash. So there we see higher frequencies, 10 to 50, because that's the multiple strokes that make up a flash. So highest frequencies between February and April, or in the autumn months, which is also a bit of bad news for the firefighters in the Western Cape. Okay, so if there are any questions, then you are welcome to interrupt me. So before I carry on, would anybody like to ask a question?
Well, the different polarities with the lightning strikes, when some which will trigger a fire and some won't.
Yes, it's quite interesting that even though we have such a low ratio of the country's lightning, the polarity in the southwestern Cape is often positive, and that is a stronger flash than a negative stroke. So they are also more rare, and you don't get them as frequently, but they have more intensity and and carry more energy and are often more dangerous actually. So even though we don't see a lot, when they do occur, then the positive strokes can be worse.
Does that mean that your ground is the positive, the earth is, what does that mean?
I'm not sure. It's the polarity of the lightning strike. So
It's like between the ground and the cloud.
Yeah, and it's different. So the negative flashes are more common than the positive flashes.
Has that changed over time? I remember as a kid growing up, I can't remember the fault lightning kind of getting more here in Cape Town.
Yeah, from what we see in the lightning detection network's data it's not really increasing.
Okay.
But yeah, the frequency is not increasing.
Just back a few slides, you have to go back. The final conditions caused by pressure, obviously, right? So low pressure will bring in. What causes the pressure system to be low or high?
So, are you talking about the thunderstorms that we see over the southeast?
Generally, meteorology generally. Why do you get a low pressure system or high pressure system?
Well, maybe I can discuss that when we look at the synoptic circulation systems. Then we can have a look at that as well.
Similar to what William was saying, is I do remember sort of in Cape Town you used to get more where you get a lightning flash in the sky, but it's not a strike.
Yeah.
So is that just between clouds or?
Yeah, so you get intercloud lightning where it just jumps between clouds, and intra-cloud lightning, and then you get cloud to ground lightning. Okay. So I must add that the lightning detection network mostly picks up the cloud to ground lightning. So if there's an increase in intercloud lightning or so, then that would not show up in the data. Okay, so let's move on to some of the weather systems that are quite typical. This is my shaky video where Renata and I were cycling near Steenberg, and you can see the nice cloud coming off the Steenberg mountain, and it's very windy. We turned that corner to Boys Drive and we just turned around again. It was a very windy day. So I want to talk about the southeaster. I want to talk about berg winds, and then also about temperature inversions, things that will affect you on your firefighting days. So with the southeaster, I have a story to tell because I was a new forecaster at Cape Town International, and there was this restaurant owner from the waterfront, and he would phone us every afternoon. His name was Mario from Bahia, and he would call us and he would say, "What is the wind going to do tonight? It's quiet." And then I would be saying, "But it's howling at the airport." And our observations at the harbour is showing the wind is pumping. It's impossible, it can't be quiet at the harbour. And he would phone again and again. And one day I just decided I've had enough of this guy. I'm going to show him wrong. And I got into my car and I drove to the waterfront. It was howling at the airport. It was howling at the harbour. The waterfront was completely calm. And that's how I encountered Cape Town's southeaster and how fickle it can be. So the southeaster has a cycle that it goes through. And usually in summer, the cold fronts don't reach us along the coast as frequently as in winter, and they tend to pass to the south of the country. And once a cold front passes to the south, then a high pressure system ridges in behind it. The circulation behind the high is anticyclonic or anti-clockwise, so that's when we get that nice southeasterly airflow around the Cape Peninsula. And a wind is given its name from the direction that it comes from. So these winds come from the southeast, so that's why the circulation is also southeasterly. And these are the days where the winds are at their strongest. But then on day 2 of the cycle, now we see the low pressure system starting to deepen over the interior, and then this high pressure system starts to move further east. That front is moving away now, and so we start to see the isobars relax a little bit here along the west coast, and if they're not so close to each other, then winds also start to decrease in places. And if we can just talk about the low pressure, so in summer, we see a low pressure system almost semi-permanently over the interior of South Africa, and that's mainly a heat low. It's driven by convection. The surface of the earth warms, it results in air rising, and that creates this area of low pressure that's semi-permanent over the interior of South Africa. And whether that causes thunderstorms or not depends on whether there's also a low in the upper air. So the atmosphere is about 8 to 10 kilometers, the atmosphere where weather occurs. The troposphere is about 10 kilometers deep. And so if there's also a low in the upper atmosphere, that's when we get unstable conditions and thunderstorms develop. But so back to the southeaster. This would then be the second day of the southeaster. So during the first day, you have these strong southeasterly winds over all of Cape Town. That's when you see the tablecloth on Table Mountain. The inversion is high, it's above mountaintop. And so winds are free to go completely over the mountain, force air to rise, condensation takes place, the cloud forms on the mountain, and as it descends on the other side, it evaporates again, so that's why it appears that the cloud is just staying there. And on these days, winds are strong everywhere, at Cape Point, in Langebaan, in Cape Town, at the harbour, at the waterfront, it's windy everywhere. But when we have a shallow southeaster, typically on the second day of that cycle, then the inversion becomes lower. Winds are not forced over the mountain anymore, and we don't see that cloud forming. That's when you get your calm days in Clifton and in the waterfront, while it's still very windy, maybe in Cape Point and in the harbour, also at the airport. So that's where the winds become patchy, because it's now determined by the blockage of the mountain. So then winds become patchy, and it's usually also becomes very windy near Cape Point, because the pressure gradient becomes tight and the isobars are very close to each other further south. Now, one of the other circulation types that's very relevant is berg winds. Now, berg winds or föhn winds in other parts of the world it depends on the coastline. So we have a coastline that's the west coast gets its berg winds from the northeast, the south coast gets the berg winds from the northwest, and the east coast gets their berg winds also from the west. So it depends on the coastline what weather system will cause berg winds. So this is the synoptic circulation that was present during the March fires. This is the 2nd of March 2015. So there was this strong high pressure system that caused northeasterly winds towards the west coast, so high temperatures, very dry conditions. But this same high caused cooler weather over the eastern parts of the country, where the easterly airflow brought in moisture and light rain. But towards the west coast, this resulted in a very dry and hot berg wind day. Berg winds along the south coast usually occur when we have a strong cold front that's causing a northwesterly airflow towards the southern coastline. This is an example of the 7th of June 2017 when we had the Knysna fires. That was an extremely strong cold front, so we see berg winds quite regularly along the south coast, not on the same scale. But here we can see ahead of the front, northwesterly winds towards the coastline, and these winds were extremely strong. So here's just another graph or another image to show you the berg wind model for Cape Town. So we have the high to the east causing easterly, northeasterly interior winds to reach the coastline, and that also causes high temperatures. And often you'll have a cold front that's approaching. Before the cold front, there's a coastal low that develops. It's a lee low that develops due to that offshore airflow towards the west coast. And this will then start traveling along the coastline, and that also frequently brings fog during the autumn and winter months when the coastal low moves past us. So that's berg winds, and now we can head to temperature inversions. So a temperature inversion is something that we see in winter almost on a daily basis, especially if it's a calm, clear night and temperatures drop, cold air sinks into the lower lying areas like the Cape Flats, and then you see a temperature increase with height. So the coldest air is at the bottom of the valley, and temperatures are slightly higher than that at the top. But sometimes we get very strong temperature inversions. And before I talk any more about inversions, I just want to show you this specific type of graph that we use in weather forecasting. And this is called a scutogram. And it gives us a temperature and a dew point temperature with height. So every day around the world at midnight UTC and at 12 o'clock in the afternoon. So 2 hours later for South Africa, 2 o'clock in the morning and at 2 o'clock in the afternoon. Balloons are released with soundings attached to them, and they make these measurements in the troposphere for the first 8 to 10 kilometers of the atmosphere. And these balloon ascents happen every day at the same time. In South Africa, we have about 3 or 4 stations that do them. Irene is one in Gauteng, Cape Town International is one in Cape Town, and then there might be some in Bloemfontein and Durban, maybe not always at the same frequency, but Cape Town and Irene are almost like clockwork done every day. And these are great tools to use when you are when there's a fire. And so I'll show you now what you can read off. Here we can see the temperature inversion is below a kilometer. So Table Mountain is roughly at a kilometer above sea level. So this temperature inversion is below a kilometer. At the surface, the temperature that we read off here at the bottom was about 12 or 13 degrees Celsius. But then at that height, just below a kilometer, temperatures were about 28 degrees at 2 o'clock in the morning. So that's a very strong inversion. And then we can also read off the dew point temperatures here. And the further apart these are from each other, that's the drier and the lower the relative humidity in the atmosphere is. And then something else that's quite useful is being able to see what winds are at different levels. So here we can see the winds were very light beneath the temperature inversion on this particular morning. So here is just an illustration of what a temperature inversion can do when there's a fire. So the temperature inversion acts as a lid. You see that the cloud or the smoke can't escape that lid that's on it. But then as the slopes start to warm up after sunrise, the inversion is broken and then the smoke can escape, and that can also result in your fires getting stronger. So that's the impact, the potential impact of a temperature inversion on a fire. You just want to look at it once again. At night time, cooling takes place in the valley, temperatures are higher above. That causes a lid on, puts a lid on anything beneath it, but then as soon as the hills warm up, the temperature inversion is broken and you get more movement.
When it releases like that, you take the lid off, it moves up. Is there winds coming in below?
Yes, so on a valley, then you will start to get your slope winds developing. So the slopes warm up after sunrise, and then you'll start getting upslope winds that will also form in the valley once the inversion starts to break. And that will also help to break up that inversion. So yes, I'm not sure if you've heard of this before. I will share all the resources that I have on the topic. But the thermal belt is really just where you encounter the temperature inversion, where that layer of warmer air intersects with the slope. So that is something that can also affect the way that a fire burns. So let's look at the diagram again. So at night, the temperature inversion forms, and this would be the warmer region that they refer to as the thermal belt, and this can influence how the fire burns. Within that warmer, drier layer, the fire will continue to burn stronger, while you will get a decrease in activity above the inversion and beneath it. So that's something that can maybe cause some confusion if you have stronger burning in one part of your slope that was not expected. So that's something to keep in mind. Let's look at a case study. Now that we have looked at all the soundings and everything, this is one that, yes?
So can I just ask you, what indicators would there be that you might get a thermal belt?
So I would say if you had a look at the temperature sounding for, say, Cape Town International Airport, that would give you a very good indication that there would be such a thermal belt. If we look at the sounding again on this particular day, that's a very strong temperature inversion. So if you hike in Table Mountain, then you sometimes feel the air warm as you ascend. So that would be where the thermal belt is positioned. And that's something that you would be able to find on a scutigram like this.
Sorry, is that data readily available online for lay people?
Yes, it is. Oh.
And one more, is that going to result then universal across a large geography?
Yes, that's another thing I can say about these soundings. So the sounding at Cape Town International Airport can be considered representative of the entire Cape Metropole. For Cape Point, for the City Bowl, it's representative, especially in the upper layers. You might see that the winds are different at the airport or the temperature is different, but with height, this is going to be quite representative of a large area. So this would definitely be applicable for the Greater Peninsula region, Cape Metropole, maybe even the Winelands as well. Okay, so looking at this case study, it's the UCT fires, and the sounding that we were looking at earlier is actually from this specific day as well. Now it's interesting to note that this particular, or part of the reason I'm looking at this case is because it was very well documented by a student at UCT. So there's the reference to the blog. I would recommend that you read it if you haven't read it yet. So he gives a very detailed lowdown of what the setup was prior to the development of these fires. So one of the things that he mentions is that this was one of those April Mays that was very dry, much drier than usual, with less than 25% of the average rainfall that occurred during that April and May. It was also much warmer than usual, where temperatures were more representative of January and February. So temperatures were much higher than usual, and it was, yeah, so the stage was set. It was very dry that autumn. And this was the synoptic circulation, so it wasn't a very strong circulation such as the strong high that we saw with the March fires. This is a much weaker high to the east of the country, not very strong indication of offshore airflow, yet we know how hot it still was in Cape Town. So despite the fact that it wasn't a very strong circulation, there was still burbuns that day in the southwestern Cape. Here are the observations at Cape Town International. So on the 18th of April, temperatures exceeded 35 degrees at the airport. John told me they measured 9% relative humidity in the game camp. The lowest humidity observed that day was in the City Bowl. That was only 10%, so that's quite close. Very low relative humidities, very high wind speeds as well. And now here are the soundings for the early morning, and this is at 2 p.m. in the afternoon for Cape Town International. So in the early morning we had the inversion, we had light winds beneath the inversion, and this was a stable profile. But in the afternoon that changed completely. The inversion was eroded and the profile became completely unstable. And that's also when we saw that the wind speeds were much higher, lower down than they were early in the morning. So this affected the way that the fire burned and behaved on that day. So typically when you have stable conditions, such as under that inversion, the fire intensity will be lower, it will be very smoky underneath that inversion because the smoke can't escape the lid. But when it becomes unstable, then you can get explosive growth in the convective column, and that can also result in just an intensity increase of flames while you are fighting. So going from stable to unstable can affect the fire dramatically. And that's when you start to get extreme fire behavior in unstable conditions, such as a high rate of spread, crowning, prolific spotting, firewalls starting to form, and a large convective column can also develop. So looking at convective columns, what's quite interesting is that they won't develop in extremely windy conditions. Convective columns can get to that great height when the winds are not very strong, but it still has to be an unstable environment. And so, just like in thunderstorms, convective columns have updrafts and downdrafts. And I showed you earlier the low pressure system over the interior develops because the land surface heats up and air rises. But the same thing happens with a fire. The low pressure, there's a low pressure that develops in the lower portions because it's so hot, the hot air rises, and that results in indrafts now moving in. So this fire is generating winds at the surface. Winds are rushing to replace the air that's rising. So that's when you start getting the fire causing winds around itself. A strong updraft develops, and that's when you can also see some cloud development above the fire. So pyrocumulus cloud can develop. And now, just as with thunderstorms, if you have updrafts, at some point you're going to have a downdraft as well. And the downdraft is very dangerous if it results in the collapse of that fire column. And that can result in a sudden increase of wind speeds at the surface, and that can also aggravate fire spreading and also endanger crews that are working close by. So there were some questions about fire collapse, and this happens. So early signs that you have to look out for before this happens would be if there is a huge fire column. That would be something to know that if there is a large updraft and a large fire column, there could be strong downdrafts eventually, because the two goes hand in hand. So if you start seeing virga would be that fall streaks with rain evaporating before it reaches the ground, or if there is actually a bit of precipitation, that would be an indication that there is a downdraft developing, because as soon as rain starts to evaporate, it cools its environment. That cold air will start to sink, and that is how a downdraft develops in thunderstorms, but also in fires. So then a strong convective column is an initial sign that there could be a strong downburst later on. And so another warning sign is if those strong indrafts suddenly stop and you have a bit of calm, and then the downdraft reaches the surface of the earth. Okay, there were also, yes?
Sorry. How is there a limitation on the size of the plume, or is there a limitation on the energy of the plume to go from the updraft and the rise to a collapse and a downdraft?
I'm not sure. Yeah, I don't know. But from what I've seen, it seems that the inversion and the mixed layer with an unstable environment does different things during different seasons. So that might be something that affects the column height as well. If it's a very hot summer's day versus maybe an autumn day where that mixed layer is not that deep, I think that could maybe play a role. Okay, so moving on to firewalls. There were some questions about that, and I'm going to draw on thunderstorm analogy once again, because it's difficult to visualize how rotation is introduced into a fire. So this is a picture that helps us visualize how rotation is introduced into a thunderstorm so that tornadoes can form. So what happens is we talk about wind shear, and wind shear is the change of wind direction and speed with height. So here we see the winds are blowing in one direction in the lower levels and in another direction in the upper levels. And this then causes a bit of rotation in the lower levels of the atmosphere, or eddies. So there is some rotation that starts to occur in this wind shear environment. And if we think about where, when you are on the mountain, that wind shear can be as a result of winds that we have at different levels, but it can also be as a result of topography. There could be a lee eddy or something that happens when winds move around the mountain. So it's almost impossible to predict this on a small scale, like in a fire, because this, especially in the varying topography that you would get on the mountain. But then the updraft, so the updraft would be here with the thunderstorm, would allow that rotation then to straighten up, so that the rotation, instead of doing this, it now starts to rotate like this. And this would happen with the fire, within the fire column, if we were talking about fires and not about thunderstorms. So the same idea applies, how rotation is introduced into a fire column. So yes, that brings me to the end of the talk, and I'll just quickly summarize what we've looked at now, and then you are welcome to ask me questions. But so there is large variability in rainfall and between seasons in southern Africa and especially in the southwestern Cape. But the one thing that we are seeing that's significant is that April-May tends to be drying out. It's becoming drier and it's becoming warmer. And that we've seen in the past 2 decades. We also see that lightning tends to occur during these same months, so the fire season might be becoming slightly longer, and also towards the end of the fire season, that's when lightning is most likely, which can act as a source of ignition. And we've also seen now what the importance of the temperature inversion is in firefighting situations. So that's something that, that you could maybe look at on scutigrams. That's available twice daily for Cape Town International. So very important to think about the atmospheric soundings that are conducted daily at Cape Town International Airport. And then also that extreme fire events are usually or are often caused by extreme synoptic circulations, extremely strong high pressure ridging, or so sometimes these are quite forecastable and quite predictable. So that should be a good thing, is that often these weather systems that result in the big fire events are actually quite easy to spot in advance. So here are some resources. I forgot to add the website for the soundings. So I will give that to John and Alex so that you can have a look at your own temperature soundings. And then a lot of the fire information about the temperature belt and the firewalls and all of that is in a very, very excellent training resource called MetEd. And that's something that is not for meteorologists alone, it's for firefighters, specifically designed for firefighters. So this is something that can be worked through. It's several hours of coursework that you can do. It's free. You just need to create a login. And then there's also some interesting reading material if you are interested in the climate, how it's changing, some good papers that you can read about local research that's been done for the area. Yes?
So you said the UCT fire was actually very well documented. Is that purely because it was somebody doing it as a study, or is it something that going forward we're going to have better documentation for this type of thing?
I think in this case it was a student who was there, who saw everything and who has a keen interest in the weather and the university, and so all of those interests combined, and I think that's what it was. It was a blog. But they then ended up doing a study, like an attribution study. They wanted to show that this specific event could be attributed to climate change. So there was actually a paper written about, and that's the last one that I show here, where they tried to attribute it to climate change. So it ended up becoming a formal study after that blog.
Can I ask the inevitable question about climate change? I'm not denying it. I'm not denying it, but say that you did already say, so autumn's becoming more of a drier, warmer thing for us, but if you look at 50 years, 100 years, where's that likely to go?
Well,
you're going to be dead, John.
the indications are that it's going going to become drier. So that's also what's in that last paper that I have there. What their findings were is that type of weather is going to become more frequent. And I think also something else that I can just say about climate change for Southern Africa in general is that people want to hear it's going to be drier or wetter, but I think what we must realize is it's going to become even more variable, like we've seen now with our rainfall seasons. Sometimes we go from a day zero drought to extreme rainfall, and those extremes are what we're going to see more often. Maybe more dry extremes than wet extremes, but we shouldn't be looking for the same weather. It's not going to be that way.
And then you mentioned something earlier about, you'll get your turn. Where, if you've got an area which is a winter rainfall area, the predictability of that compared to like a dry winter or an area that gets summer rainfall, you said there's a difference, difference in how predictable they are.
So the seasonal forecasts tend to be better for the summer rainfall region than for the winter rainfall region. And it's because, it's difficult to pinpoint it. Different things influence the same region's weather together, but there seems to be more skill in seasonal forecasts for that region than for the Southwestern Cape.
Jane over his mouth, good Chris.
Yeah.
Some of the weather forecasting sites allow you to choose between the different models, like GFS and ECDW or whatever. And they can often be very different. And it might just be anecdotal, I found the European model to be better here for the Western Cape. I mean,
I tend to agree. When I use the windy or whatever, I will also select ECMWF. But it has a higher resolution also. So
it's quite a lot smaller.
So that
was not going to be my question actually. What one do you recommend specifically here for the Western Cape?
I like to use ECMWF as well.
And is that consistent between winter and summer?
Yes.
Because I tend to look at the weather more in summer. Winter, I just assume that it's going to be
I usually use the higher resolution ECMWF.
Okay, John, you can continue.
With the inversion layer, if you had to look at the graphs over like a 30-day period, would that layer be at the same level during the time of day? Is it pretty consistent, or is the inversion layer, does it move around quite a lot? You can't really predict sort of a December is going to be here at this time and here at this time.
It's very variable. As I showed with the ridging high that causes the southeaster, just between those 2 days, you'll see a very big difference in inversion heights. So it's something that changes a lot and quickly.
Sorry, just a tangent question on Paul's question. In terms of the weather apps, when we all use Windy or Windguru or YR.no, they all have merits. Which do you find to be your go-to?
I prefer Windy because I like the maps and I like to decide for myself what's going to happen. And I don't use the point data often. I won't necessarily look at Cape Town's forecast. I'll just get a general idea. But I also like Windguru for wind. Windguru uses GFS data, which is a bit coarser resolution than the ECMWF data that we get on Windy. But I think those are my two ones that I prefer.
John, in planning, traditionally what we've always done is if they've got a fire, let's say Ocean View, we'll check Simonstown, Fishhook, Noordhoek, and then we'll check Windguru, Windfinder, and just see, if they all agree, then we're like hundreds. If there's a sudden change, and we're like, okay, well, Santa Cruz, and we're not sure why, but, there's a conflict. So, we often in planning will like to check multiple sources and just see if they all correlate. So I have another question. We often see winds going in two different directions on the fire. Like literally, John's got a great video where the smoke is going this direction at his feet and the rain is going this direction at his, I mean, that was quite an extreme one. Is there a way to know in advance that we're going to get such, or is that more created by the topography?
It could be the topography, it could be the fire itself that creates those small scale wind changes, but sometimes you will see that on this, when you look at the vertical profile of winds on a security ground, then you would see that at the lower levels it's southeasterly, but higher up it's northwesterly. That often happens here in Cape Town.
Yeah, because I mean, thankfully, just because I suppose we know Cape Town, we know how the topography affects the different winds. So we know if it's a southeaster, depending on, as you said, how strong it is. You know, Camps Bay fires could be really pushing down to the ocean, whereas other times. But yeah, sometimes it's just impossible just to tell us.
Has there been any noticeable increase in the number of northwesterly or cold fronts impacting the Cape Town area in the winter, in the summer, in the last 20 years or so? Because it seems like we're getting more northwesterly or cold fronts, prefrontals hitting when there are major fires going on than before.
I'm not sure about that. I would say I don't think so, but yeah, that'd be interesting, because northwesterlies could also be caused by coastal low pressure system, even though the front maybe moves to the south. But yeah, I don't know.
You said the extreme weather conditions are quite predictable. How far ahead can you predict it? Sort of a week, a day?
Yeah, I think a week is maybe a good, just put it out there, see there's something that looks quite significant a week out. 5 days, I think models are becoming quite accurate. 5 days and shorter periods than that. I would say 7 days is still quite a stretch. But it could be maybe the front won't hit in the morning. Maybe the timing will be different. And sometimes with some weather systems like cut-off lows, a lot of change still happens in that week. But there usually is something so it can be good for a heads up a week ahead. But the closer would be about 3 to 5 days.
Yeah, in winter the rainfall, and I just look here from Newlands because that's where we are. Often if you look out 5 to 7 days, it's often massive amounts of rainfall predicted, which then dissipates very, very quickly, and that seems to be quite common. Am I correct?
Yeah.
Is there a reason for
7
that?
days out, it's just still a lot of. It's a good guess, but and you could maybe say it's going to rain the weekend, but then to keep a close eye on it, 3 to 5 days. That's usually when it starts to settle. Models start to settle on the forecast and remain.
And not weather related, but the balloons that you release twice a day from Cape Town Airport, do they have to be coincided with when flights are taking off and landing?
Yeah, they have to call, get permission from the ATCs to release. It's a bit of a process.
And cost and that, because I mean that's surely a single use. It goes up and disappears somewhere.
It's expensive.
Lands on a farm somewhere.
No, it is. I think that's why we don't have many ascents happening in South Africa. It's because of the cost. And it's also helium to fill the balloons or hydrogen. Yeah, it's expensive.
So you said looking at the synoptic charts and the high and low pressure systems is a good way to forecast when extreme fire behavior might go. So are there any resources where it gives a forecast of those charts? Because I know South African Weather Services like at 6 in the morning and 6 like 12 hourly.
Yes.
But like, are there forecasts of those?
No, that would be observation charts. So that's also what I showed you here. You can get them from their website, but that would be too late to use as a forecast.
Yeah.
But if you use windy, then you can overlay mean sea level pressure, and that would give you a similar map to use as a forecast. Maybe I can ask a question about inversions and the things that are mentioned here. Is that relevant? Is that something that you've encountered, and that unstable fires on unstable days, fire columns?
Yeah.
Is that something that?
Yeah, I mean, a lot of that stuff, like the collapse, and Chris was just poking me when you were talking about that collapsing pyrocumulus of Castle Rock at the beginning of the season.
Okay.
We were on the opposite side of the mountain. We were watching this forming, and he was going, that's getting big, that's getting big. And next thing we saw on the radio was like, guys, we need you to come around. And
Sure.
we were told to abandon what we were doing because everything had just, gone to pieces on the other side of the mountain when that actually collapsed.
Yeah.
And also, just before that, you could see all this swirl, fire swirl all over the place. It was becoming very weird.
So you had warning signs?
Yeah.
Yeah, I mean, we were literally watching because we were working on the western side of the mountain ridge in amongst the farms on Plateau Road. But the fire that was on the eastern side, we could actually see this massive column forming. And where we were, it was actually very benign.
Yeah.
It was actually. And then when that collapsed, then the radio just went mad, and we were actually pulled out and sent around. And,
Yeah. Inversions aren't taken note of a lot by fire services, but they have a massive impact. The weather around the UCT, or the game campfire, the Whiskey fire, it's quite fascinating because as I was asking about that possible collapse, there wasn't really a pyrocumulus that I could see, but there was a plume, and then you had this weird topography. And then John was there, and he basically said they couldn't fly the helicopters there. It was very smoky, couldn't see, and then you had this what almost was like an outflow boundary of wind pushing everything across Rosebank. So I've been fascinated since then to find out, because I was running around all over the place looking. I was fascinated to know, was it a plume collapse? Was it just a topography influencing the wind dynamics that took that fire, and the wind drove the fire across down, into Rosebank and caused all the mayhem?
Do you think it might have been when the inversion broke that could have been what happened? That was the point where
The thing is, the wind came down slope. So if the inversion broke, the wind wouldn't have been pushed down slope across the freeway.
Well, it would suck.
So it would be sucked. So the inversion was pushing out. So the
yeah,
inversion collapsed.
but
and
when
plume
the
went up.
inversion collapses, it allows the winds that are higher up now to also reach the surface. So it could result in a sudden increase in wind speeds.
Yeah, I'd be very interested to read that.
Looking at the column, is there a way to understand which way it's going to collapse? Or is it just the kind of the wind direction higher up?
Yeah, I don't know. I think if it's a neat column, then I guess you can see it quite clearly. Then I think that the collapse will happen where the updraft is, but it should be quite close to that actual column itself.
I've checked a couple online, and there was that one you sent me from Portugal where it just went, but then it just fell over, and the other ones seem to. I don't know if there's a pattern.
Kind of seen out Badabu, when it collapsed there, it collapsed away from us and just chaos.
Yeah.
So you can't, I guess, there's no way of kind of figuring out which way it's going to start to. Exactly.
How?
That bit one of their shaped to it, but it was kind of
going away, yeah.
It was going that way, so.
Could it? How different would the sort of signs that you see be between that inversion lifting and something just like a very strong cut-off low, where a lot of the fires we've had, basically it's prefrontal conditions, the wind's blowing, but then it sort of comes to a stop, and then it doesn't really know where it's going, and then it just comes the opposite direction, really hard and heavy. We had that sort of, what makes me think of that is if you look at the direction of the fire moving and the cloud plume moving, and if you go back to the 2015 fires in Turkey, same story where you've got a 180-degree wind shift over a very short period of time. Could it be a combination of those, the inversion and just a very steep cut-off low? or not?
Yeah, I think the one weather system that comes to mind when you're talking about a rapid wind shift, and you said it was the March fires in 2015, right?
Yeah, so that's one of them. The UCT fire had something similar, but the March 2015 was, if remember, we were going up to Kai and we were going there, and the wind literally, when Ryan made that call to evacuate us, and there were 180 degree shift that came straight down, and very intense flames, fire whirls, that kind of thing. We had evacuated that. We even went in. We had to start evacuating houses and stuff as well.
Yeah, what I just want to say is that the coastal low is notorious for sudden wind changes. So if the coastal low, with the game campfire, we also had a weak coastal low, but it was there ahead of the cold front. And so there was also a shift in cooler onshore airflow. So that's something that happens very suddenly. It's offshore, and then suddenly onshore. So that could cause a sudden wind shift. And with the March fires, this low was also traveling down the coast. So I don't know if that maybe caused that sudden, because then winds would go from northwest to southwest when a coastal low moves through. And you would then also almost immediately feel a temperature change. It becomes cooler onshore air. But yeah, I don't know.
Are there any planning people here with clever questions? Emma.
Lauren. My question's all done.
Who's been asking the clever?
Can I ask you a lightning question?
Yes.
Do we get sprites over South Africa as well?
Over?
South Africa as well, or do they happen in particular areas of the globe?
I'm not sure. No, usually they are very high, and I wouldn't. I'm sure they would occur here too. But
Okay.
We have a monitoring station in Sutherland for sprites, so I imagine it's there for a reason.
Okay, so newbie question, what's a sprite?
Yeah.
Sorry.
No, I know we have a monitoring station. I don't know what that is.
this is like a very fibrous lightning above cloud tops. It's,
Okay.
It goes kilometers up.
Yeah,
So it starts at the clouds but goes up instead of down.
yeah.
Okay.
Just quite fascinating.
So, with your coastal low, is that the same as a cut-off low, or is that different?
No, it's a very shallow surface low pressure system. So it's really in the lowest hundreds of meters in the atmosphere. So it's a very shallow system, and it often comes with fog in the autumn months. It brings that sudden, you can go from a Bergwind day, and then in the evening you see the cloud coming in over Table Bay and the fog, and that shift in when the cooler air comes in. So that's a coastal low. It's a shallow low pressure system, and it won't show up higher in the atmosphere. A cutoff low is a low pressure system from the surface all the way up to 8 or 10 kilometers and much higher maybe. So it's a very deep connected low pressure system, and that's what gives it enough instability to create storms and rain and adverse weather.
So is that what the weather bomb they sometimes speak in America, where they like look at hurricanes or something, where you've got it's like 960 in the center of the hurricane or something, and then normal sea temperature is like what, 1 minus
It's like the pressures, yes.
Yeah, is that...
It won't be as low, but what I also mean is that with the coastal low, that's a good example of a low pressure system that's really just confined to the surface. But when you look at weather, you look at the whole layer of the troposphere. So that's where all the weather occurs, in the lowest, say, 10 kilometers of the atmosphere. And when you have a cutoff low, then you can see that low pressure system at all the different layers in the atmosphere. So we look at the 850 hectopascal layer and the 500, and that low will be there all the way through. But the coastal low is just at the surface. It can't be seen higher up.
Is the coastal low not the extreme? The extreme is the cut-off flow.
Yes, the coastal
Coastal
low
low
is
will
very
just
benign actually. It's
We
yeah,
like it.
yeah, we like it. Well, we like cut off
We do.
flows
Not if
too.
you like
Our
it.
minutes, we like yeah.
Okay, so any yes?
No, this isn't a question, this is a comment. So I found scuti diagrams on Windy, if anyone's interested.
Yes, you can also generate model scuties. So you
Yeah, I
can
think it-
forecast
yeah.
scuties as well. And I'll share the link for the observation scuties.
Okay. Last chance for questions before we set Lynette free.
I have a question, but it's maybe not directly related. I'm actually also interested in UV radiation, so obviously it's definitely not that field, but would you be able to give us some link maybe where we can actually look at it?
Wait, sorry?
The UV exposure, I'm quite interested in that.
I think the Weather Service gives an estimate of that on their website, but and I think some stations in South Africa measure it, but I am not sure how to access the observations.
What?
You're in Africa now, put a hat on. Not in France anymore.
It's extremely high.
Yeah, the issue is that we won one of the highest exposure in the world with Australia, and I was amazed. Short story long. Anyway, we're looking at that through a family member of mine having some issue with skin cancer potential. And you speak to the dermatologists and you listen to them, you're supposed to be covered from head to toe. We have one of the highest in the peak season of our firefighting.
Yeah.
And that's actually what makes me think is, we send the guys actually out there to fight fire. And in the meantime, we're also exposed to massive amount of UV radiation.
So there's also that whole ozone hole and that kind of stuff.
So we'll talk to me to stand down and be
Yeah. Okay, before Chris starts showing more family things and photos of the grandchildren and stuff, thank you very much. I think everyone here will agree that was really fascinating and it's right on point to what we're working with. So thank you very much. And then for you and Rad, there are forms on the way out where you can sign up.
Cool.
Okay.